أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Today we will be talking about the review of thermodynamics law. This includes the basic understanding and the revision of the old concept. So this lecture is a part of the lecture series from the course of thermodynamics, having the course code of PHY331. Basically, we need to, before discussing the zero law of thermodynamics, we need to discuss the first law of thermodynamics that often gives us the concept of energy conservation. And according to the first law of thermodynamics, it is clearly described that energy cannot be created nor destroyed. Of course, we can convert, or we can from one form of energy into another form of energy. So this is actually the first law of thermodynamics gives us the concept of energy. The second law of thermodynamics gives us the concept of entropy, while the zero law of thermodynamics gives us the concept of temperature. Zero law of thermodynamics states that two bodies, if it is individually in thermal equilibrium with a third body, then the first and the third body and the second and the third body are also in thermal equilibrium to each other. So this is actually the this slide describes the first law of thermodynamics, and it basically describes the concept of energy, depicting that energy cannot be created nor it can be destroyed. Therefore, the total amount of energy of the universe is a constant quantity. So it means the total energy is always conserved. So energy can, however, be converted from one form to another form, or transferred from a system to the surrounding, or vice versa. So we can convert energy from one form to another forms, or transfer from a system to the surrounding, or from the surrounding to a system, depending on their temperature difference. So we have some spontaneous process that spontaneously occurs. This is actually in natural directions, just like this. In this example, some spontaneous process is shown, where there is two tubes that are connected with each other with some wall. One is represented by tube A, another is represented by tube B. So the tube A is evacuated, and tube B has a certain pressure. So initially there is a wall, or there is a barrier, or there is an obstacle in between the two tubes. When it is removed, the barrier is removed, so what happen? The gas will move from higher pressure toward the lower pressure, or toward the gas will move from B to A, and this gradient depends upon the difference of this pressure. So after settlement, both the tube will have the same pressure. If the initial pressure of tube B was 1 atm, so the final pressure of tube A and B will be 0.5 and 0.5 atm. So this is the spontaneous process. If you want to follow, or if you want to do this process in the back direction, if you want to extract the pressure from one tube and want to evacuate it just like it was before, so and bring the same pressure to the initial tube B. So is it possible that it can do spontaneously? The answer is no, because some process occurs spontaneously, that is in direction of nature, or the gradient, or some other thing is the driving force for that. But in this case, if you want to evacuate the one of these tube, so some energy will be required for that. So keep in mind, this is not a spontaneous process to evacuate one of the tube among the two tubes. But when two tubes are connected and one is already evacuated and pressure goes from one to another, this is a spontaneous process. So the gas in vessel B will spontaneously effuse into vessel A, and but once the gas in both vessels, it will not spontaneously occur the process. We have another spontaneous process. That is actually the process that is actually in one direction, and that is actually not spontaneous in other direction. Just like if we have a, mm, a metal rod, so a metal rod where it its surfaces become oxidized due to the reaction with the atmosphere, but if you want to clean it, so automatically it will not occur. So it is not a spontaneous process, but the first process was spontaneous process. We have some other spontaneous process, that is a process that are spontaneous at one temperature and may be non-spontaneous at other temperatures. So just like above 0 degrees centigrade, it is spontaneous for ice to melt. I mean, if the temperature is high, the ice will melt automatically, and the ice will melt automatically. But below 0, the reverse process is spontaneous. I mean, if the temperature is below 0, so what happen? The water will automatically convert into ice. So this is the reverse process. So we have some spontaneous process in one environment, and spontaneous process and some spontaneous process in other environment. We have some reversible processes and irreversible processes. A reversible process basically depicts that a heat that is initiated from one place come back to the same place, or a process that is initiated from a single point come back to that point without any loss of energy. So in a reversible process, the system changes in such a way that the system and surrounding can be put back in their original states by exactly reversing the process. So this is the normal thing, how the temperature or the heat is transferred from one body to the surrounding, from a body towards the surrounding, and then the same heat goes from the surrounding toward the body without any loss of energy. But this is, keep in mind, this is an ideal process, and reversible process in reality are not possible. So changes are infinitesimally small in irreversible processes. We have irreversible processes, and in irreversible processes, so that are all spontaneous processes are actually irreversible processes. Similarly, all real processes are also irreversible processes. So irreversible process cannot be undergone by exactly reversing the change of the system. Just like we have a piston where there is a gas and vacuum, so there is a piston, movable piston. So when the piston is allowed and it moves in the other direction, so the gas expands. So if you want to move back the piston to its original position, so what you need to do, you need to do some work. So it means that the system that is initiated from a single point, the gas is expanded as pressure become lower. But if you want to bring the piston back to its initial position, we need to expend some energy at that. So that is actually irreversible processes, and all natural processes are irreversible processes because some sort of energy is wasted. We have this is the concept of first law, Newton and the thermodynamic first law, that if you want to provide a heat to a system, so part of that heat will be utilized in doing work, and part of that will be utilized in increasing the internal energy of that system. So we have the entropy of a system that could be actually described by the second law of thermodynamics, and we already discussed in the initial slide that second law of thermodynamics gives us the concept of entropy. And entropy is a term coined by the Clausius in 19th century, and it was convinced by the significance of the ratio of heat delivered and the temperature at which it is delivered. So entropy can be thought of as a measure of the randomness of a system. So it is related to the various modes of motion in a molecule, just like for energy, for the total energy and enthalpy. H, entropy is a state function, therefore del S is equal to S final minus S initial. So for a process occurring at constant temperature, For a process occurring at constant temperature, an isothermal process, del Q is equal to Q in the amount of heat divided by T, where Q reversible is the heat that is transferred when the process is carried out reversibly at a constant temperature, and temperature is T describe the temperature of the system, that is described in the unit of energy, in the unit of Kelvin. So second law of thermodynamics could be described in the using the concept of entropy, and that basically describes that the entropy of the universe can either remain constant or it should increase. Entropy of the universe could only be remain constant if we can consider these processes to be reversible processes, but normally in reality the reversible processes are not possible and it is not occurring. So that is why the entropy of the universe is increasing, and it means that we are losing useful form of energy. So we are moving toward the heat death. I means the energy is if you want to complete a cycle regarding the second law of thermodynamics, part of the energy will be converted into work and part of the energy will be wasted, and it will be given to the sink. So that energy is given to the environment, and that is wasted. So I means in order to complete a cycle of a thermodynamic system, of a second law of thermodynamic systems, you need some part of the energy will be wasted. So the second law of thermodynamics states that the entropy of the universe does not change for reversible processes, and it increases for spontaneous or irreversible processes. So the entropy of the universe increases just like for real and spontaneous processes, but entropy decreases for individual processes. So this is some equation that says that for reversible or ideal process, the del S of universe is equal to the del S of the system plus del S of the surrounding, and that should be equal to each other. That it should be equal to each other and equal to 0. But if we consider irreversible processes, just like real and spontaneous processes, so for that the del S of the universe should be equal to del S of the system and del S of the surrounding. So this should be equal to each other, and it should be greater than 0. So this should be greater than 0. So this basically states that entropy of the universe is increasing and we are losing useful form of energy. So this equation says. So this is some entropy change in a particular system. Here we have gases. So in general, entropy increases when gases are formed from liquid and solids, and liquids or solutions are formed from solids, and the number of gas molecule increases or the number of moles increases. So this is some general circumstances where liquid is because we normally see that atom in the crystalline solid are often in regular periodicity, and there is low randomness in that. So that is actually the crystalline structure of that material. But when it is converted into liquid, so I mean the randomness occurs in that, and the crystallinity is modified. So that is why it sees that liquids and solutions are formed from solids. So that's in that particular case the entropy of the system increases. We have third law of entropy, third law of thermodynamics. We already discussed the first law of thermodynamics, second law of thermodynamics. Now it's turn to discuss the third law of thermodynamics. And the third law of thermodynamics says that entropy of a pure crystalline substance at constant at absolute 0 is equal to 0, and we cannot achieve the 0 Kelvin temperature. And as regarding the equation, it could be written as S is equal to K natural log of W, as K natural log of 1 should be equal to 0. So if we see at 0 Kelvin, S is equal to 0. So increasing the temperature, it should be greater than 0, and the entropy should be also greater than 0. So I mean there should be an increase in entropy of that particular systems. This is the simple case describing the third law of thermodynamics, that the entropy of a pure crystalline substance at absolute 0 is equal to 0. So S is equal to K log omega, that describes this equation, or K is equal to natural log of natural log of 1 should be equal to 0. So we have entropy on the vertical axis and we have temperature on the horizontal axis. So we have both phases, three phases. One is the solid, liquid and gases. So we see what happens when the material is transformed from one shape to another shape. I mean, when the material is transformed from solid to liquid, and then finally is transformed from liquid to gas, and so there is a melting and the boiling occur, so that gradually increase the entropy of the system. Let's see on the vertical axis, that is actually describe the entropy of this particle. So the first stage is the solid, when we are transforming the solid into liquid. So in that particular case the melting occur, and the melting gives us an abrupt increase in the entropy of the system. Looking here, we can see that there is abrupt increase in the entropy of the systems. So when we are increasing, so here the entropy of the system drastically increases when we are moving in the liquid line and increasing the temperature of a liquid. So there is a gradual increase in the entropy, but a point occurs where the liquid start boiling. So at boiling there is a huge increase in the entropy of that particular system. So because the liquid is converted into gases, so there is an abrupt increase in the entropy of the system, and finally we can get higher entropy for the gases. So this figure basically describes that entropy of solids and liquid is often smaller than the entropy of gases, and the entropy of the systems increases, or any particle, any solids increases when we are bringing it from solid to liquid and then gaseous form. So no, yes, so this is something about there are molar entropy values of substance in their standards. This is actually some of the molar entropy value or the standard entropy of some of the gases. Just like we have H2 gas, its entropy is 130.6 joule per mole into Kelvin, and if we have nitrogen gas, its entropy is 191.5 joule per mole Kelvin. And then like we have liquids, his entropy is definitely, if you're looking toward the entropy, his entropy is 69.9 joule per mole into Kelvin. Similarly, if we take the solids, then entropy is gradually reduced, and for the solids the entropy is 29.1 for lithium solids, and is joule per mole into Kelvin. Similarly for sodium chloride is 72.3 joule per mole into Kelvin. So this is some entropy. So standard entropy tend to increase with increasing molar mass of this substance. So we have practical use of this entropy. Entropy changes in the surrounding. So heat that flows in or out of the systems also change the entropy of the surrounding. So if we have an isothermal process, so del S should be equal to minus Q energy of the system divided by T. So some other practical is the increase in the entropy of the universe, and that describes that if we want to describe the entropy of the universe, then the universe is composed of the system and surrounding. So therefore the total entropy should be the sum of the entropy of the system and entropy of the surrounding. So del S universe should be equal to del S system plus del S surrounding. So if we consider some spontaneous processes, so del S universe should be greater than 0. But if we consider reversible processes, so del S universe should be equal to 0. But keep in mind, reversible processes are often a type of ideal processes, and this process does not occur in reality. In reality we have spontaneous process, or we have some process that are actually irreversible. I mean, we can, when we bring the system from one point to another point, so there is often some loss of energy, and this of loss of energy goes to the heat death. So therefore we are losing useful form of energy, and scientists are trying that, as we have limited sources of energy, so scientists are trying for some renewable sources of energy, because the existing sources of energy are limited and we are losing useful form of energy. So this is something about the first law, second law and third law of thermodynamics. So thank you very much for